So this is the 2D or not 2D. That is the question. Yes, I'm going to repeat the joke again. So, okay, 2D or not 2D with position, vector, and acceleration. Okay. Motion in real life occurs in 2 and 3 dimensions. If motion were in 1 dimension, again, it would be very boring. Okay, so if we launch something, boy, that went further than I wanted to. But, so let's step back. Okay, let's say we want to launch a projectile. Okay, say a potato cannon, or a what? Don't launch a potato cannon. Can you? I am sure you are capable of doing it. Please don't. At least not at my behest. Or if you're firing some other sort of projectile, let's say you want to join the artillery. Okay, you will be launching a projectile. You'll be launching a projectile towards an unfortunate target. So, it'll go up, and then because it will experience the effects of gravity. I am assuming that we are assuming this is on the Earth or some other celestial body that has a ground. Okay, it will follow this path, and for most intents and purposes, the ground will be flat enough to disregard the curvature. So, we launch a projectile, and this is the X direction. That is the Y direction. Okay, let's say we start initial position at 3 meters from the y-axis. Okay, this isn't good enough anymore. Okay, to describe the motion of the object. Okay, the object could be out there in space, where a green dot is. It could be anywhere but. Okay, it could be here. It's no longer along the x-axis for a particular length of time. We are now traveling through a second dimension. Right. Okay, so what are we going to do with that spot? How are we going to communicate it? Okay? Now, unless you have something that specifically says the magnitude and direction of the vector, it is much more practical to leave things in rectangular coordinates. And so we are going to identify this point, okay, where it is in space with respect to the origin. That's what WRT means. WRT is with respect to the origin. Okay, so our position vector begins at the origin and extends to our position. Starts at the origin and extends from the origin out to our position. That is our position vector. This just identifies where it is in space, not how it got there. Okay, and we will call that R from our last lecture, that its derivation comes from the radius, because anything with that length is going to be that same distance from anything with that length would create a circle around the origin of that distance. Okay, now Ri has two components to it. It has Rx initial. Okay, so follow the notation here. It is Rx initial I hat direction. So the value of it is Rxi, and it is in the I hat direction. Okay, that's that vector. Right? That one there is Rxi. plus RYI, RY initial, in the j hat direction. These are the components to make up our vector R. Okay, but then we have a final position, and it's over here. It's right there. So we've gone from RI, our initial position, to our final position, right there. And that'll be our final position. And we'll label that with a RF for a final vector. You may see where we're going with this. RF now has its own components. It is RFX and RFY. RXF and RYF. Okay, in its components are RXF I hat and RYF, RY final, J hat. Okay, now you may be anticipating where we're going to go next. Okay, now if this is an actual problem, we would be getting values. Remember, we'd be getting actual numbers for RXI, okay, RX initial, RY initial, RX final, RY final. Okay, but this is in general terms. So our object changes position. What do we call a change in position? We call it it is a displacement. So we are going to find the displacement as our object travels from our final position, from our initial position to our final position. And there it is. This right here. Well, that's cool. I think I like the green hand better. There we go. Okay, so this is our displacement starting from our initial position going to our final position, and we will be able to calculate what that vector is. Okay, so continuing with that drawing. So what is our displacement? Okay, our delta R has a delta R in the x direction, and it has, okay, which is given by that little dude right there, by that dude. This is delta R in the x direction, and it's going to have a delta R in the y direction, which is right there, going up. No, right there. Okay, so our delta R in the x direction, delta R in the y direction are shown. And so delta R has a delta x I hat, and it is delta y j hat. It is the change in the x direction I hat and change in the y direction j hat. Those are the values. Well, obviously x and y are in the I hat and j hat direction, right? So why are we putting delta x I hat and okay? Because you're going to be putting numbers there. Okay, and so we're doing this to make sure that you keep putting the I hat and the j hat to make sure that when we do put numbers there, you still have that habit. Okay, so why do we do I and j? Because those are values. They're actual numbers. So, what is delta R going to equal? Well, it's going to equal the differences in the individual components. So, it's going to equal R final x minus R initial x. The initials and the directions can be switched. So as long as you're okay, so it could be RXF minus RXI, or it could be RFX and RFY, whichever. That doesn't really matter as long as you're as long as you're being consistent within your statement. Okay, but our x components are still I hat, and our y components are still j hat, and what that winds up being is just the changes in each one of them. Okay, now it took time to do this, did it not? Not just to write it down, but it actually took time for the object to move from one position to the other, from our initial to our final. So that would imply that it is going to have a what? It's going to have a velocity, because our displacement divided by the amount of time that it takes to do that is going to give us a velocity. And our average velocity is, of course, given by our displacement divided by our time. Delta r divided by delta t. But what's really going on here is that we are doing this for each and every component. And we are allowed to break this up into each and every component because they are independent directions along any particular axis. Okay, and they don't affect each other, and that allows them the orthogonality of these vectors of our components allow us to do individual mathematics on each one of them. Okay, and this is a key idea right here. Okay, it's exactly the same as what we were doing before, but now we're doing two directions at the same time. Okay, and this is key. These are at the same time. If you are going to come up with your components with respect to time, that as time passes, you're going to have an x variation and a y variation with respect to time. Okay, so our average velocity is going to equal delta r over delta t, which in this case equals delta x over delta ti and delta y over delta t j. Right, and here we go. Now we're coming up with, we're actually moving into the realm of parametric equations. Guys remember those? Good times. Okay, now to really get complicated, or not, perhaps to simplify, okay, if we take the limit as our delta t approaches 0, then delta r delta t really becomes dx dt I hat plus dy dt j hat. Okay, and now we have instantaneous velocity terms for v. Okay, and that is our velocity at any moment in time. Okay, oh, and by the way, when we do that, okay, that does become dr dt is the sum of dx dt I hat and dy dt j hat. All right, and so our total vector becomes our velocity in the x direction, I hat, and our velocity in the y direction, j hat. Okay, so what if our velocity is changing? Okay, and we go through the same process with all of these guys too. So let's say we have, this is our motion. This is our position track. Okay, it's not a what? Function. It's not a function. Okay, so we have to come up with some other way of analyzing this. And the best way of doing it is through our vector analysis. So we'll call these guys v initial and v final. Okay, so we start off in this direction here, and we finish off in that direction there. Yeah? Okay, now mind you, these are not, those are the velocities at that particular point in space, right? Okay, so at this place, is traveling off in that direction. This place is traveling down in that direction. The actual vector math to this is far more complicated than what we're going to be going over today. Okay, this is some hardcore. Okay, there's actually is some pretty nasty parametric equations, and you to really analyze it, you need a third dimension, and it's ugly. But for our purposes today, for graphic analysis, it's fine. Okay, we're going to find delta V. So we're going to take VI and plug it down here and put it at the... So to find delta V, we're going to move our initial velocity over to the tip of our final velocity, or to the tail. We're going to match the tails up. Okay. Which is actually better if we match the tails up, because what are we, in order to find our delta V, we want to subtract them, right? Yeah. And so if we subtract them, well, whoa, slow down. It started taking off on me. I guess I didn't save the, okay. So, if we have VF minus VI, right here, if we have VF minus VI, that's the same thing as VF plus a negative VI, which would be that direction plus that direction, which still gives us the blue delta V right here. Yeah? Okay. Or another way we could write this is we could write that VF equals VI plus delta V, right? This is the delta V equals those guys. So move the VI to the other side. So VI going this direction plus that delta V is going to give us our VF right there. Yeah? All right. So in that case, what was our acceleration vector? Our average acceleration vector? Well, it would be in the same direction as our change in velocity. Okay, it would just be how much time, divided by our change in time. That would be our acceleration. Okay, so whatever our change in velocity vector would be, that would be, divide that by time, and that's our acceleration. Okay, so VF minus VI over delta T. All right, and then we start breaking this down exactly the same way, that our average velocity is going to be our Vx final I hat plus Vy final j hat, okay, minus Vx initial I hat minus Vy initial j hat, okay, or they'll just wind up being the deltas for those. So delta Vx I hat plus delta Vy j hat. All right, so you subtract the components, you subtract the x's, subtract the y's, and you get your deltas. Okay, your change in velocities, and then it's all that divided by time. So what's coming next? Okay, if these are all deltas and this is our average acceleration, then when we take the time derivative of it, or when we set the limit of this delta t to equal 0, well, I didn't get that I had in there, did I? I forgot to draw that. Okay. So as we take the limit as delta t approaches 0, our velocity and our time is going to equal our acceleration in the I hat direction plus our acceleration in the y hat in the j hat direction. Okay, and this is in the same direction as our delta v vector. If you have a direction to your change in velocity, that is the same direction as your acceleration. Okay? And that is the end of today's lecture.